So today we'll be starting with this is the chapter on circles. Now last year you've done circles and this is an extension of that. It's much simpler when you compare it to class 9. So what are the terms involved this year? There are two basic terms that we have to know. What is tangent and what is a secant? So if I am going to draw a line from an external point such that it touches the circle externally at a point, then that particular line is called a tangent. Okay, so this is a tangent because it is touching this circle at one point. And suppose I draw a line intersecting the circle at 2 points, then that is called a secant. Okay, so this is a tangent. It intersects the circle at one point. This is an external point P. And this is called a secant because it intersects the circle at 2 points. Right? So this extends, and this point is actually called the point of contact. This point is called the point of contact. So hope this is clear. A tangent is a line drawn from an external point P touching the circle. Okay, touching the circle externally at a point. So it's a line which is passing outside the circle, just touching at one point externally. And this point of contact is very important because the first theorem says that the angle between the radius and the tangent at the point of contact is 90, right? So that we'll be doing just now. And this is a secant intersecting the circle at 2 points. So once you understood what is a tangent and secant, we go to the first theorem. The first theorem says that the angle between the radius and tangent at the point of contact is 90. So if I'm going to have a tangent here, okay, the tangent is going to touch the circle externally at a point. And let's assume this is the center. So if you're drawing from the center, joining to the point of contact, then we have to prove that this angle is 90. So let us assume that this is a tangent AB. This is the point of contact P. So what we need to prove is that angle between the radius and the tangent at the point of contact is 90. So the first exercise we will be using this theorem. Angle between the radius and tangent at the point of contact is 90. So that means we have to prove that OP is perpendicular to AB, or we can say that angle OPA and OPB are 90 degrees. So how do we prove this? We are going to do a construction. Let us assume that there is a point here. Okay, we are going to, from the center of the circle, we are going to join it to a point C. Okay, construction. Take any point on the tangent AB. Take any point on the tangent AB. Okay, and join to the center O. Join to the center of the circle, that is O. Okay, so that's what we are doing here. We are taking any point on this AB and joining to the center O. So how can we say that this angle is 90? Now look at this figure that we have got. It is clear from the figure that OC is greater than the radius. OC is greater than the radius. Okay. Let us assume that the radius of the circle is R. So it is clear that OP is equal to the radius because this is the radius line drawn from the center to the circle on any point on the circumference. That becomes your radius. So OP is equal to the radius. And OC, if you see, is extending beyond the circle, and therefore we can say that OC is greater than the radius. So what is the conclusion here? Hence we can say that OC is definitely greater than OP. Okay, OC is definitely greater than OP. Now suppose I am taking any line, I am taking any point on AB and joining into the center O, that will obviously be greater than OP. So OP is the shortest possible distance from O to the tangent AB. Okay, so this is the conclusion. What is the conclusion? That if I take any point on the line AB and join it to the center of the circle O, that will always be greater than OP, because that will always go outside the circle, isn't it? So therefore we can say any point taken on AB, any point taken on AB when joined to O will be greater than OP. So hence what is the conclusion? That OP is the shortest possible distance. OP is the shortest possible distance from O to the tangent AB. Okay, OP is the shortest possible distance from the center of the circle to the tangent AB. And what is the shortest possible distance? It is always a perpendicular. Therefore, OP is perpendicular to AB. Okay, so this is a very clear thing. So if I'm going to take a point here, if I take OP, I take OQ, OR, all this will come greater than OP. OP is the shortest possible distance, and which is the shortest possible distance? The perpendicular. We can keep on taking on either side. This will always be greater than OP. Right? So hence we conclude the first theorem that the line drawn from the center to the point of contact will always be a perpendicular at the point of contact, or we can say that angle between radius and tangent at the point of contact is 90. So using this now, we can solve the first exercise on circles. So the first question there is, how many tangents can a circle have? How many tangents can a circle have? If you are having a circle, this is a tangent, right? You can draw a tangent here. You can draw another tangent here. You can draw another tangent here. You can draw a tangent here. You can keep on drawing tangents, because what is a tangent? Tangent is a line which touches the circle externally at one point. And the circle is made up of how many points? A circle is made up of infinite points, right? So each point of the circle, we can draw a line touching that particular point. So if there are infinite points on the circle, through each point it is possible to draw a tangent. So how many tangents are possible? We can say that infinite tangents are possible. So answer to the first question, how many tangents can be drawn to a circle, or how many tangents can a circle have? We can say a circle can have infinite tangents. Okay, then we go to the second question, fill in the blanks. A tangent to a circle intersects it in dash points. A tangent intersects the circle at how many points? It is very clear from the definition of tangent itself that tangent will only touch the circle at one point. So the answer is 1 point. A tangent touches the circle at 1 point. A line intersecting a circle in 2 points is called, now if this is a circle and it is intersecting the circle at 2 points, then that line is called a secant. So answer to the second part will be secant. A circle can have dash parallel tangents at the most. If you have a circle, this is a tangent, this is another tangent, these can be parallel. But if I try to draw more parallel tangents to this, either it will come outside the circle or it will come inside the circle. So this is not a tangent, this is not a tangent, because this is a secant and this is a normal line. So when you talk about parallel tangents, how many parallel tangents are possible at one point of time? Then the answer is 2. Okay, it can have 2 parallel tangents only at a given point of time. Then, of course, here the cases are many. Okay, you can have parallel tangents like this, you can have parallel tangents like this, you can have parallel tangents like this, but at a given point of time, we can only have 2 parallel tangents. So don't get confused You may argue that this is also possible. But at a given point, in one case, if you take case A, B, C, at a given point, it is possible to draw only two parallel tangents. The common point of a tangent, this is a tangent, the common point of a tangent to a circle, and the circle is called, this point is called what? This is the common point, this is called the point of contact. Okay, you can note this, this is called the point of contact. So that's question number 2. Then we go to the third question, question number 3. A tangent PQ at a point P of a circle of radius 5. Okay, so we are having a circle of radius 5 and the tangent is given PQ. So this is a tangent touching the circle at one point. The radius of the circle is given 5. Okay, so this is the radius that is given 5. This is the line drawn from the center to the point of contact P. So center of the circle is given O. Tangent is PQ at a point P of a circle. P of a circle. That means that this is point P of a circle. It is part of the circle. The external point is Q. The value of OQ is given 12 centimeter. The radius is given 5. And the question is find out what is the length of PQ. We have to find this. Now this is where we are going to use that theorem that angle between radius and tangent at the point of contact is 90. So I can say that angle P is 90 by the theorem, right? If angle P is 90, we can use Pythagoras. Now remember, when we use Pythagoras, the hypotenuse should be alone. So 12 square is equal to, 12 is the hypotenuse. Okay, this is 90. This is not the hypotenuse. OQ is the hypotenuse. So 12 square is equal to 5 square plus x square. 144 minus 25 is equal to x square. So 119 equal to x square. So x will be root of 119. So your answer will be x is root 119. So as per the question, the option number D is your correct answer. Okay, some people just do 12 square plus 5 square equal to x square. There you will get the answer as 13. That's wrong because the hypotenuse should remain alone. So hope this is clear why this has been taken alone, because this is the hypotenuse. And the last question of that exercise, draw a circle and two lines parallel to a given line such that one is a tangent and the other is a secant. So this is our circle. We have to draw two lines parallel to this such that one is a tangent and one is a secant. So by definition, we know that angle between radius and tangent is 90. So the best way to do this is that from the center of the circle, I'm going to draw a line and this becomes my point of contact, or this becomes my point of contact. If this is the point of contact, I am going to construct 90 here because I know that angle between radius and tangent is 90. So when I construct this 90 degrees, then this is my tangent. This is going to be my tangent. I'll take any point inside this. Okay, I can take the center or any point inside, and I'm going to construct 90 degrees here. Then this will become a secant, and this secant and tangent will be parallel to each other because we know that lines perpendicular to the same line are parallel to each other. So this is also 90, this is also 90 to the same line. So this is going to be parallel. Now you can take any point outside, external point, construct 90 degrees here. So this is neither a tangent, this is neither a secant, this is a normal line. This is also 90, right? So when you construct 90 degrees with respect to the same line, what do we find? The conclusion that the line, the secant, and the tangent all will be parallel to each other. So as per the question, what was it? That we have to draw a circle that we have drawn. Two lines parallel to a given line. So this was a line such that one is a tangent and one is a secant. So we have drawn the line, we have drawn the tangent, we have drawn the secant, and all of them are going to be parallel to each other. So that's the first exercise. Then we have another theorem that I will be explaining to you in the next video. That is, tangents drawn from the same external point to a circle are equal. Okay, that is the theorem that we'll be doing next.